Thank you all for joining us. For those of you who don't know me, my name is Lucy Tomasini. I'm a project manager with the Grower Group Alliance and the Southwest WA Drought Resilience Adoption and Innovation Hub, which is quite the mouthful and is more easily known as the Southwest WA Drought Hub. So welcome to the third iteration of our Building Resilient Farming Systems webinar series, where we highlight 6 of our projects in our transformational program. So the webinar today is brought to you by the Southwest WA Drought Hub, which is led by the Grower Group Alliance. So before we go into the project, a very quick introduction to the hub, who we are and what we do. So the hub has been around since 2021 and is part of 8 hubs nationally, funded through the Australian government's Future Drought Fund. So the aim of our hubs is to provide regionally relevant information and support to help farmers and regional communities prepare for and adapt to the impacts of drier, warmer seasons. So we very much focus on collaboration in the agricultural ecosystem. We bring together researchers, agribusiness, grower groups, industry leaders, government, and so forth to make sure that agricultural research is impactful, accessible, and to drive innovation. So through funding from the Future Drought Fund, we sought project EOIs from hub consortium partners that investigate concepts that contribute to evolving agricultural systems in Western Australian agriculture. So each of these projects is led by a hub consortium partner and delivered in collaboration with growers, grower groups, industry experts, regional organizations, to make sure and help ensure that the work is practical and relevant and grounded in real-world farming contexts. So while the primary focus of these projects is on generating new knowledge, tools, and approaches, some innovations may over time contribute to broader shifts in how agricultural systems operate and build resilience at multiple levels. So today we'll be deep diving into a very innovative project, which is led by Whole Green Foods. So our presenter today is Nick Stamatiou. He is the CEO and co-founder of Whole Green Foods. So this project explores how byproducts from the potato processing industry can be sustainably transformed into novel livestock feedstock. So helping unlock value from waste, strengthening circular economy opportunities, and supporting on-farm productivity and resilience. So Nick recorded his session today, but he'll be available for the Q&A at the end of the presentation. So just before we get started, a few housekeeping things. Please make sure that you are on mute. There'll be a Q&A at the end. So if you have any questions, there's a Q&A tab at the top. Please feel free to write your questions there and I can either ask them for you at the end or you can pop your hand up and ask them yourselves. This webinar session will be recorded and it will be put up on our webpage at the end or from next week, so you'll be able to rewatch it then. So without further ado, let's get into the presentation.
Thanks everyone for attending today. We found this project really interesting and I hope that I can share some of that with you. So anyone who's spent time around processing facilities knows that potato processing generates a substantial wet waste stream. It's part of the operation. You can't really avoid it. It's peel, it's offcuts, rejected material, second-grade potatoes, and it moves pretty fast. The reality is it's difficult to handle. It's around 85 to 90% water. That means it's heavy and it doesn't store well. It starts to deteriorate really quickly, and from an operational perspective, disposal is often the simplest path because time matters in a processing environment. We get that. But when we looked at that stream more closely, what stood out to us wasn't the inconvenience. It was the fact that nutritionally, there was nothing wrong with this stream. It still contains carbohydrate energy. It still has feed value. In many ways, it's not that different from the grain we're feeding livestock elsewhere in the system. So the question that started this project was a practical one. Are we discarding this material because it lacks value or because it's physically and biologically awkward to work with? And if it's the latter, then maybe the opportunity isn't about inventing something new. It's about removing the constraints that are preventing that value from being realized. So what we set out to test was pretty simple in principle. Can we take this wet, unstable waste stream, engineer around the moisture and the bacteria, and convert it into a feed input that actually makes sense in a real agricultural setting? And that's really what this project focused on. So if we zoom in on how the current system operates, it's actually very efficient at producing food. Potatoes come in, they're peeled, cut, processed, packaged. The core product moves through the line quickly and cleanly. But alongside that product stream, there's a secondary stream that moves just as quickly, and that's the waste, the peel, and the offcuts. Now, the challenge isn't that this material is unusable. The challenge is that it's wet and sometimes pretty dirty. At 85–90% moisture, you're essentially moving water with some solids in it. That creates immediate logistical constraints. It's heavy to transport, it can't sit around for too long, doesn't stockpile neatly, and because it's biologically active, deterioration starts almost immediately. From a processor's perspective, you're not in the business of waste valorization, you're in the business of producing food efficiently. So disposal becomes a practical solution. But when organic material like this is buried or sent to landfill, decomposition generates methane. And methane isn't just another emission, it's significantly more potent than carbon dioxide over shorter time horizons. Now, I'm not raising that from a policy standpoint here. I'm raising it because it means that a stream containing usable feed energy is being converted into an atmospheric gas. At the same time, in another part of the system, livestock producers are buying barley or other grains to supply carbohydrate energy to animals. So there's an inefficiency built into the structure of the system. We're discarding energy in one location and recreating that energy in another. That inefficiency isn't obvious when you look at, say, an individual business, but when you look at the supply chain as a whole, it becomes pretty hard to ignore. And that's what prompted us to ask whether the barrier here is truly value or whether it's just moisture and microbiology. When we started looking at this more closely, it became clear that this isn't really just a processing issue. It sits inside a broader set of pressures that most people in this room are already experiencing in one form or another. The first is feed volatility. Grain pricing isn't as predictable as it used to be. Drought cycles, export demand, fuel costs, they all feed into input pricing. For livestock producers, carbohydrate energy is a major cost line, and when that moves, margins move with it. The second pressure is emissions, and not necessarily because producers want to talk about emissions, but because increasingly regulators, customers, and supply chains do. Methane from landfill and methane from livestock are part of the same conversation. Whether we like it or not, that scrutiny is increasing. The third pressure is simply efficiency. Agriculture has always been about getting more value out of the same land, the same water, the same inputs. So when you see a nutrient-rich stream being discarded like this, the question naturally becomes, is that inefficiency acceptable long term? Now, none of these pressures on their own would necessarily justify a project like this, but when they converge, feed volatility, emission scrutiny, and resource efficiency, they seem to create a window where waste to feed conversion starts to make more practical sense. Not as a theoretical sustainability exercise, but as a way of improving system resilience. And that's really the lens we approach this through. If we can stabilize and dewater this stream effectively, we're not just solving a disposal issue, we're potentially creating an alternative feed input that strengthens the broader system here. Now, it's important to point out that our proprietary Winx technology, it wasn't developed for potato waste. The core focus of our work is actually improving the functionality of whole food ingredients, looking at how to unlock nutrients inside plant matrices without heavy refinement or extraction. At a technical level, Winx uses controlled energy input, cavitation, and mechanical forces to rupture the plant cell walls. Inside plant cells, nutrients and water aren't just sitting around freely. They're compartmentalized, structurally bound, physically trapped often. Most conventional processing methods can reduce particle size, but they don't necessarily disrupt that internal structure completely. What we began noticing during early development work was something pretty interesting. Materials that were normally resistant to separation behaved quite differently after Winx treatment. They filtered differently, they pumped differently, and in some cases they even dewatered more effectively. And that observation stuck with us because if water is structurally trapped inside plant cells and Winx disrupts that structure, then in theory it should change how moisture behaves during separation. And that's what led us to ask if the main barrier to valorizing potato waste is moisture, not nutrition, could Winx fundamentally change how that material handles? So this project wasn't so much about forcing Winx into a new market. It was about testing an observation. Does the technology alter the physical constraints enough to unlock a viable pathway? One of the early realizations was that this wasn't a single variable problem. You can't just solve moisture and ignore microbiology. You can't solve microbiology and ignore feed formulation. And you can't solve both and ignore how feed is actually delivered on a farm. So when we structured the project, we deliberately did it as a cross-disciplinary project. Hull led the Winx processing, obviously, trial design and overall integration. Aquila Scientific worked with us on microbial testing and risk assessment, particularly around Bacillus cereus. Ace Livestock Consulting supported feed modeling and helped us understand realistic substitution limits in ration design. Thomson Redwood provided practical insight into how feed is delivered and handled in real systems, because a technically workable ingredient still has to fit into existing infrastructure. And Simplot and Bandotti grounded the project in operational reality by providing access to actual waste streams and real processing constraints. That combination mattered because if this was going to move beyond just a lab concept, it needed to hold up technically, biologically, nutritionally, and logistically, and all at the same time. When we started characterizing the waste in detail, the constraints became very clear. The first constraint was physical. Potato peel waste isn't uniform. Steam peeled skins behave very differently from cold peeled skins. Steam peeling gelatinizes the starch. That makes the material sticky and paste-like. It blinds filters almost immediately. Water is effectively locked into the starch matrix. Cold peeled skins retain more cellular structure, but they're still extremely high in moisture. In both cases, traditional dewatering approaches struggled. Vacuum filtration failed pretty quickly, and mechanical separation didn't remove enough water to materially change handling characteristics. So physically, the material resisted processing. The second constraint was biological. At 85 to 90% moisture, you have an ideal environment for bacterial proliferation. Testing identified Bacillus cereus as the dominant organism in the streams that we analyze, but that's not particularly unusual in wet agricultural waste. But it does mean you can't simply redirect the material into feed without stabilization. So at that point, we had clarity. The problem wasn't a lack of nutrients, it was water and bacteria. And unless we solved both, there was no viable pathway going forward. We addressed the biological constraint first. Working with Aquila, we evaluated stabilization approaches that would be practical in a feed context. We weren't looking for lab sterility. We were looking for stability within real handling timeframes. So we implemented a combination of organic acids, acetic, propanoic, and formic acids, which are already widely used in feed preservation. The objective was simple, to suppress bacterial proliferation sufficiently to allow safe handling and integration, and that worked. The treated material demonstrated controlled microbial growth over the relevant timeframes. So at that point, we had removed the biological barrier, but the physical one still remained. So the turning point in the project was really dewatering. We ran side-by-side comparisons between untreated waste and Winks treated waste under vacuum filtration. Untreated material blinded the filter surface pretty quickly. Water remained trapped within the plant matrix and very little separation occurred. That result reinforced why this stream is so difficult to repurpose. Then we applied Winks and the treated material behaved very differently. Filtration was possible. We were able to produce a semi-solid cake with moisture in the range of 58 to 62%. Now that might not sound dramatic on paper, it's still wet, but operationally it's transformative. Reducing moisture from 90% to 60% changes transport economics, handling characteristics, and system compatibility. More importantly, it demonstrated that the structural constraint, that is the way that water was bound inside the plant matrix, could be altered. That was the moment the hypothesis was validated. Winks didn't just change nutrient availability, it changed how the material behaved physically, and that was key. Once the material was physically and biologically viable, we tested whether it made sense nutritionally. Working with ACE, we modeled feed rations for weaner and grower pigs. We substituted Winks treated potato material for barley in the ration. The modeling showed that up to approximately 20% barley replacement was achievable while maintaining macronutrient balance. Heavy metal testing confirmed aluminium levels were within acceptable feed thresholds. So this wasn't just filler, it functioned as a legitimate carbohydrate energy source, which means we weren't just reducing waste, we were displacing conventional grain. We also wanted to understand the emissions implications properly because there are two very different pathways here. If the waste goes to landfill or burial, you're effectively taking organic material and letting it break down anaerobically. That tends to generate methane, and methane, as everyone here knows, is a big part of why organic waste disposal is increasingly being looked at. Not because farmers are suddenly trying to be ESG, but because it's simply inefficient for carbon to leave the system as gas. The alternative pathway we modeled was stabilize and process the waste, then use it as a feed input that displaces a portion of the grain. So you get two effects working at the same time. One is avoided methane because the waste isn't decomposing in landfill conditions. The second is displaced grain production because every time you replace a portion of that barley in a ration, you're offsetting the emissions associated with growing, harvesting, and transporting that grain. When we ran the modeling, the estimated net reduction came out to around 0.68 tons of CO2 equivalent per ton of potato waste processed. Now, if you can run this as a practical processing pathway, and that's the key condition here, then you're not just solving a disposal problem and not just creating a feed input. You're also improving the emissions profile of the system, and that matters because it means the solution has multiple value streams. It's got operational value for processors, feed value for livestock systems, and a measurable emissions benefit that increasingly affects downstream supply chains. Once we saw that the technical and environmental case could stack up, the next question became very simple. Can this actually work logistically in the real world? This is where things get real because it's one thing to show that something is possible, it's another thing to make it workable. The central logistics truth here is simple. You don't want to transport water. At 85-90% moisture, moving untreated waste any distance at all becomes quickly very expensive. Even if the material has feed value, the freight can wipe it out. So the most viable pathway is co-location. In other words, processing needs to happen either at the processor or very close to it. So you're reducing moisture and stabilizing the material before it becomes a logistics problem. The second integration question is what type of feeding systems can realistically take this material? So you're trying to push it out into traditional pelletized feed systems, and you're going to start to run into moisture tolerance limits. Pelletizing generally wants dry inputs, and once you start talking about drying, you shift the economics and the energy profile pretty significantly. Where it becomes much more practical is in liquid feeding systems or systems that can handle higher moisture inputs, provided microbial stability is controlled, which is why the organic acid work that we did mattered so much. So when we say logistics determines viability, what we really mean is co-location is not nice to have, it's fundamental. And the adoption pathway is most realistic where existing systems can accept moist feed inputs without requiring major infrastructure change. This is also why it's important not to treat waste to feed systems as a single technology problem. It's a supply chain design problem. You have to solve for where it happens, how it's handled, and who touches it. And once you accept that the winning model is co-located and operationally integrated, then the next layer becomes what are the practical engineering levers that decide whether it's a nice idea or a viable asset that can deliver value. So if I step back and summarize what we actually learned, not just what worked in the trials, a few things really stand out. The first is that the barrier to value was never nutritional. The material already had feed energy in it. What prevented that value from being realized was physics and biology. The second is that dewatering is the economic lever. Every improvement in moisture content changes handling, storage, transport, and ultimately the cost of adoption. If you had to pick one variable that decides whether this works at scale, it's that. The third is that integration needs to be designed around reality, not around how we wish the system worked. You can have a technically impressive process, but if it requires major changes to how processes operate or how the feed is delivered, adoption is going to become slow and very expensive. So in terms of what's next, the pathway is pretty clear. We've shown feasibility, but feasibility isn't the finish line. The next step is live feeding trials. The modeling we've done gives confidence around substitution potential, but feeding trials are what tell you about animal performance, feed acceptance, and any operational issues that only show up when you have real conditions. In parallel, there's also work to do on the engineering pathway, specifically what an industrial dewatering and handling system looks like when integrated into a processing site in a way that doesn't add complexity and labor. And then there's the expansion piece. We're currently proposing an extension of this work through the End Food Waste CRC, looking at cattle trials in South Australia. That's important because ruminant systems are obviously quite different. The nutritional dynamics are different and the logistics can be different. And it also broadens the potential market and adoption pathways for this technology. So the roadmap from here is not abstract. It's prove it in animals, prove it in the operational integration, and then scale in the environments where it naturally fits. So in closing, this project didn't start as a big statement about circular economy. It started as a practical question. There's a wet waste stream that's hard to handle, but it still contains feed value. So are we throwing it away because it's genuinely useless or because it's just difficult? What we've demonstrated is that the constraints are solvable. We can stabilize the biology. We can change the physical behavior enough to dewater it. We can model real substitution potential in feed rations. And there's measurable emissions benefit if the deployment model is done properly. The remaining work isn't about proving the concept again. It's about proving the pathway. Animal trials, site integration, and scaling in the places where logistics make sense. And if we can do that, then potato waste stops being a disposal problem and starts to become what it always was, a nutrient stream that just needed the right handling. Thanks for your attention today, and I'd be happy to answer any questions that you might have. Thanks.
Amazing. Thank you very much for that, Nick, for that super insightful presentation. It's great to hear about the challenges that you've taken from this project and also the learnings. Such an exciting project and such exciting work with multi-level benefits All right, let's go into the Q&A session. If you have a question, feel free to put your hand up. I might start us off with a question that we received online. So, Nick, how does a potato grower supply this waste? Would they go through a washbackers or take product directly from the farmers? Is a question we received.
Yeah, typically we've worked with the potato processors. I think that's the way it works best, just in terms of managing bacterial load as well. I mean, going through that process, whether it be steam peeling or mechanical peeling, it does clean up the ingredients significantly. So in terms of the co-location model that we've proposed, I think that's probably where it belongs best. Perhaps the only thing it doesn't capture is the potatoes that might not make it off the farm in the first place. But I think if there was a use for those potatoes, then they would make their way downstream.
Great, thank you. I might ask another one we received, just for those who might not have been able to attend today. How is the nutrient content measured and maintained?
I think measurement, I mean, this is probably more a question for Tony. It's fairly standard measurement of the nutrition, just the way you do it in human feed nutritional panels. But in terms of how it's maintained, I mean, the acids, the organic acids that we've used are very standard in the feed industry. So all the work that was done shows that it's preserving the nutrition, stabilizing the ingredient enough and for long enough that you can get it downstream and feed the animals with it.
Great, thank you. All right, we've got some questions in the chat from David and Lynn. Would you, either of you, like to ask a question, or would you like me, or I can read it for you? I'll just go ahead and read it. So David's asking, with the CO2 emission reduction, is this based on full life cycle analysis or only the gates of landfill and grain feed offsets?
Yeah, the latter. Yeah, we didn't do a huge amount of work on that, so it was a fairly restricted measurement. Yeah. It wasn't really the objective of the project, but you can definitely see that there's that advantage. Yeah.
Yep. Great, thank you. And Lynn is asking, will a financial cost benefit be investigated in the proposed EFW project, e.g. nutritional benefits by replacing barley vs cost of the value-added potato feed?
It's being proposed in the project. We still don't have the sign-off on that project yet. So all the partners are being brought together. We've got Simplot on board as one of the industry partners. I guess before we even get to that point, it's figuring out, do the same benefits exist in livestock as they do in pigs? That's the unproven part. I mean, we've had really good success in pigs, but very different animals, ruminants. So the first challenge is to see if it's adding value in livestock, and then obviously we'd like to perform that work as well. All the trial work is being proposed out of Struan in South Australia, just because they have probably a better setup than we do over here for doing those sorts of research trials. But yeah, in terms of, I mean, desktop feasibility, it seems to make sense, but we won't know until we get out there and try and do it.
Great, thank you. Kind of following on from that, we received a question about if this technology is applicable to other vegetables and fruit waste.
I'm assuming that's in the context of feed. I mean, yeah.
Yeah, but yeah.
I mean, we deal, our core business, as you may have got from the presentation, is not so much in animal feed. We work with all sorts of ingredients. So we've done, say, 450 different ingredients, and looking at how we can two things: really minimize waste by making it really small, and secondly, by the technology ruptures the cellular structure of the plant cells, and what that does is liberate the nutrition and the bioactives within it. So yeah, on that basis, you could apply it to any fruit and vegetable, really. The part I'm not qualified to answer is more around what's that going to do in the animals, how much benefits going to have. Something like potato, you've got hydrolyzed starch, which it clearly benefits pigs. Other stuff, I'd need some guidance. Yeah, in terms of whether it would work. We're doing a bunch of work with grapes at the moment. That's one, especially with the contraction of the wine industry, that might be interesting to look at from a feed perspective. But yeah, I mean, if anyone has any suggestions, we'd be happy to look into it, or perhaps we've already done the preliminary work on it.
Yeah. Great, thank you. David, you have your hand up.
Yeah, sorry. Yeah, thanks very much. A really good presentation, Nick. Really informative, I thought, and direct. Just a couple of queries. One is what sort of TRL you'd be rating your technology at this stage, noting that it was existing technology, I guess. And the other being the 30% reduction in water. Is that currently recovered, or what is done with it? Thank you.
Yeah, TRL, I mean, definitely for food applications, we'd say we're TRL 9. I mean, commercially, we're moving into a deal with one of the major plant-based milk companies. So our tech, I mean, much bigger than the one you can see on the screen there, but that'll be used to do up to 60 million litres of plant-based milk a year. So yeah, definitely TRL 9 for that application. I mean, that's probably the most complex one we do. So I'd be saying around, yeah, TRL 7, TRL 8 for anything else, and it would just be optimizing and tweaking the process and some of the upstream stuff. We do have a particle size restriction in the system, so nothing that I consider to be a massive technical risk, but you'd have to have some pre-processing to get it down to a certain particle size before it goes into the winks. But yeah, we haven't deployed any systems like this for animal feed. Your second question about water, we've only done it in pilot scale, so it definitely is recoverable. We just did vacuum filtration. There might be other technologies which could get the moisture content down to, say, 40-50%. It's just that trade-off. Is it worthwhile, and what's the energy cost going into it? But I think absolutely you could recover the water. I mean, we could have done it in the pilot process that we did.
Great, thank you both. Does anyone else have a question? Anyone else would like to put their hand up? I think we've covered the ones in the chat. We did receive another question online around what would be the avenue for commissioning such a processing facility in WA, which is quite a big question.
It's a tricky one to answer because it depends on what infrastructure, what equipment you already have available to you. I mean, it's the potato processors have pretty efficient lines for peeling the potatoes, and the only issue I see is that the waste currently is not treated as an ingredient so much. So you could definitely improve on that side of things and just minimize bacterial load. But yeah, it wouldn't be that significant. I mean, you're looking at a system like the one on the screen with some bigger pre-processing tanks in it. All the heating and cooling stuff that we have there would be unnecessary for this application. So yeah, I don't know. It's going to depend on the operator and what they've already got. But in terms of cost, again, yeah, I mean, you're probably looking at about $1 million maybe to set up something like that.
Yeah. Great, thank you. Bruce, you have your hand up.
Yeah, just a point of clarification, really. Have you done actually feeding trials with pigs, or is it just desktop study?
Oh, we have, yeah, not in Australia. We've done some early work in South Africa, where my co-founder said it was from. So we have done that work. But yeah, we were trying to replicate that and look to do that. The original sponsor of the work in Australia was Australian and Pork Limited, and so they were proposing a piece of work which didn't go ahead. So yeah, we were hoping for some additional funding to extend this project to validate the work that we'd already done in South Africa, but we were seeing increased growth rates of up to 7% in some cases. Yeah.
Yeah, and I suppose a follow-on question or comment is that, as you said before, the price of grains goes up and down. So while you might be putting 20% in now, there may not be a market for it next year if the price of barley comes down. So it's
it depends how you want to view this technology. I mean, all the stuff that we do in human consumption is really, it's not about dewatering at all. It's about nutrition. So it's by breaking the cells open, you can liberate that nutrition and make it more bioavailable. So you can view it as a dewatering tech for potatoes, and it's definitely what it is. But at the same time, it's creating a more bioavailable feed. So it's got the ability to turn anything into a more bioavailable feed. So I'm not saying you'd run barley through it necessarily, but I don't think it's a technology that you would just leave there if the barley prices came down.
Great, thank you. Any last question before we move on? All right, I think we've had many great questions. Thank you very much, Nick. Thanks again for such a great presentation. It's really, really exciting to hear about your work, and I think we're all very excited to see where it's going to go next and how you prove the pathway with such multi-level benefits. So really, really great and really insightful. So thanks for joining us today. Thank you all for joining.
If anybody wants to reach out for more information, you can share my contact details. I'd be happy to have a chat to anyone and answer further questions.
Amazing. Thank you very much, Nick.